This conference will now be recorded.
Okay, great. So the conference will be recorded. Okay, guys, do you see my screen with the slides? Can someone say yes if it is so?
Yes, everything perfect.
Yes. Okay, great. Okay, then welcome to the second lecture. I'm still in this Corona self-isolation. Welcome to my kitchen. So, and today it is a second lecture of the course, and today we will talk about dependability. So I will tell, or let's say I will go through the main concepts of the dependability, because if you will Google dependability, you will find, this heap of terms like reliability, safety, fault, error, failure, maintainability, availability, security, resilience. All these things, they might be a little bit different in different communities, but there is a general theory that defines all these words, I would say, all these terms. So, and we will talk about so-called dependability theory, and basically I would say the main picture describing what is dependability, this what you see on your screen at the moment. It is so-called dependability tree. So, and dependability, it's a kind of a group of system attributes such as availability, reliability, safety, confidentiality, integrity, and maintainability. Dependability deals with three kinds of threats that the system can be exposed to, such as faults, errors, and failures. And the main idea to develop the means to improve the system dependability, and there are four kinds of means, such as fault prevention, fault tolerance, fault removal, fault forecasting. So this theory was proposed by the guys from UCLA, University of California, Los Angeles, some years ago. So, and there were Avicinis and Lapri. I'll tell about that later, but well, why I don't have the video here, because I should have the video. By some reason it's not here, and I have to use the YouTube to show it, because at the beginning of the lecture I am trying to show you something. So, and this is the descent of the zone, which is called Secuirty. So, and the idea was that, and this is basically the video how it should be done. So the zone has been centered and should be landed to the surface of Mars. So, and now it shows how it enters the Martian atmosphere. The parachute should be deployed at some point, and then at some point the parachute should be, kicked out, and the zone should be landed using these thrusters. So, and this is how this should be done, and there is a beautiful video of the European Space Agency about that. However, since we are talking about, dependability, failures, and so on, the Secuirty indeed landed to the surface of Mars, and it landed here, but the problem that it also landed here, and here, and also some part of it has been landed here. So, long story short, it was landed not in one piece, but in many pieces. What has happened? So the lander has so-called inertial measurement unit. It is basically a sensor that estimates, the position and the acceleration of the unit in space. The accelerations of three angles and on three axes, and also angles. there was a fault on the sensor, and the sensor became saturated. And saturated means that it is unable to take some higher readings. So the saturation also was coupled with the data from navigation computer generated the altitude reading that was negative or below the ground. So basically it was sensor fault plus software fault, and these faults together tell the vehicle that the altitude is negative, meaning that we are already on the ground or we are even under the ground. So because of this, the vehicle thought, okay, I'm already landed, and it cut off the parachute and this back shell, which you have saw in the video. And the braking thruster then was fired for about 3 seconds rather than 30 seconds because it's already thought that it is already on the land. The problem that it was not on the land, and basically this was done on the altitude of 3.7 kilometers, and then it was impacted the Martian servers at quite high speed, 540 kilometers per hour. So it was of course unmanned mission, but let's say it was quite expensive, 230 million euros. Well, so this is one more example of the failures. Now let's go to the theory, which might be a little bit dull and boring, but I'll try to make it to some extent interesting. As I told, this dependability theory, it was proposed basically by two guys. It's Jean-Claude Lepre from France and Algirdas Avicenius. Originally, he's from Lithuania, but he worked in UCLA, University of California, Los Angeles, US. And the first guy, he's already passed away. The second one, he is working as emeritus professor in UCLA. So, and basically before them, there were, a lot of different terms such as, fault tolerance, failure, fault, error, dependability, reliability, safety, things like this. Basically what the guys did, they grouped all the things together and presented as a kind of a fine defined theory. And this theory was well accepted. And now most of the companies basically follow this terminology. If you are interested, I recommend this book. It's really a small one, Dependability Basic Concepts. But the lecture basically consists of the parts of this paper, also basic concepts and taxonomy of dependable and secure computing. So, and let's say all what you will see in the lecture can be found either on the book or on this paper. Okay. First, let's define what is dependability. So, dependability of a system, and these guys, they were mostly defining it for the computers, so they defined like for the computing system, but now it's for the system in general, is the ability to deliver service that can be justifiably trusted. What does it mean justifiably? It means just we are able to provide some justification that the system that we can trust to the service of the system. So it's not only that the system is reliable, but we also can prove that the system is reliable, and that's what this word justifiably here means. So able to be explained or shown to be reasonable with good reason. So, and it is the ability of the system or ability of the service that system delivers. So, and the second also definition, which is also used, is the ability to avoid failures that are more frequent and more severe than is acceptable. I mean, every system fails. The question is how often, or let's say, we all know if we buy a mobile phone, it will die at some time, but we hope that it will, it will at least last a couple of years. And that is like, or that by dying, it will not, it will not blow up and damage your head. That's what we are saying about severe and acceptable. Like we accept that it will fail at some time, but according to the requirements, so it will fail later than sooner. Okay, now let's come back to this tree. Dependability attributes, it's a group of attributes, it has threads, it has means, and also, let's say, there is quite complication with translation of these two different languages. So I'm originally from Russia. I tried to translate it to Russian. There also strange thing happens. Here is, let's say, official translation of this term to German language. So, for example, in common language in German, we will call everything like Fehler. So, but here it is fault is a Fehlerursache, errors is Fehlerzustände, and failures is Ausfälle, and the things like this. But let's say English terms are well accepted even in German companies, so we will continue with English terms. And we will start with the first group. Let's talk about threads. There are three kinds of threads: faults, errors, and failures. So faults are defects in the system. Errors are incorrect internal states. And failures is incorrect delivered service. I will go through these several times more during the lecture and you will get the difference. Now I'm just giving some short definitions. Now about means. Fault prevention means to prevent the occurrence of the introduction of fault. Like when we are developing the system, we need to prevent the faults that will be inside the system. So fault tolerance means to avoid failures in the presence of faults. The thing about these faults, errors, and failures is that faults is something static. I mean, for example, there is a bug in the code and this is a fault. As soon as we are not executing the code, everything's fine. But if we execute it, because of the fault, we could have an error. For example, erroneous signal will be sent, wrong data, this is an error. And when the system stops provide correct service, then it is a failure. So, and this fault tolerance, it means, okay, we accept the faults in the system, but the system is robust not to propagate the faults to failures. I mean, okay, for example, we have some wrong sensor reading, but in the system, we have a special checkup of the sensor readings that will, detect it and say, okay, we should not trust it, and the system, our system will drive or fly somewhere, so without any damage. This means fault tolerance. We have a fault, we might have error, but we don't have fail. Fault removal, it's how to remove the faults from the system, and fault forecasting is basically to analyze the system and predict the future incident and predict the consequences of the faults. Now, more interesting things about the attributes. There are 6 classical dependability related attributes. They are listed here: availability, reliability, safety, confidentiality, integrity, maintainability. In most cases, we will talk about reliability and safety, but let me give definition for the other things. Availability means readiness for correct service. Like, your web service is available 24 hours per day, seven days per week. It means that the system is ready to provide the service, and this is availability. The system is available. Reliability, it means the continuity of the correct service. It means that when the system starts providing service, the service is reliable. We will not have, outages, or the system will not shut down or something else. So it is the ability of the system to continuously provide the correct service. Safety, it is everything about harm to the people or environment. It means even if the system will break down, it should not harm a person. So that's why, for example, we are talking about the safety when we are driving the car. We need to use the belt to drive safe. Even if something happens, we will stay safe. Same for the planes and the things like this. So Also quite interesting thing. I mean, the system could be 100% reliable, but not safe. So for example, we have a truck, autonomous truck and the goal or the service of this truck is to move some goods from point A to point B. It could be perfectly reliable. It will deliver the service. It will take goods from point A and drive with them to the point B. But by the way, it can hit some cars and it can damage some property or some people. In this case, the system is reliable but not safe. And vice versa. The system can be perfectly safe but not reliable. For example, we are sitting in the car and the car is broken. We cannot drive from point A to point B, but we are perfectly safe. So this is the difference between reliability and safety. Confidentiality. Absence, it's about, it's about security. Absence of unauthorized disclosure of information. Integrity, absence of improper system alternation. It means that, let's say, the hacker cannot hack in the system and change it in the way it shouldn't be changed. And maintainability, the ability of the system to be repaired if it is in a broken state. So in this course, okay, today we will, I will talk a little bit about the system security, because this confidentiality and integrity, it has something together with system security, but it is different concept. And there is basically 2 points of view. Let's say there is a point of view from dependability community to security and the point of view of the security, and this is quite different. I'll explain it later. So as I said, today we will talk mostly about the reliability and safety. So Lepre and Avicenna, they defined this theory, and after that the theory was accepted, and now it is used in industrial standards. And there are some safety standards. For example, there is an example of the general safety standard IEC 61508, and here in Germany also well-known standard ISO 26262. This is automotive standard. So for example, if you want to develop some controller and sell it to BMW, your controller need to be certified according to this standard ISO 26262. Otherwise, BMW will not use it on board. So in this tree, you can see it is maybe a little bit off topic, but I'll go through it. There are standards and the organization bodies who develop the standards. The oldest one are these three: International Organization of Standardization, ISO, IEC, this one, International Electrotechnical Commission, and there's also International Telecommunication Unit. So these guys are basically developed the general standards. Then there are also standardization organizations depending on the communities, for example, Society of Automotive Engineer or Society of IEEE, Institute of Electrical and Electronics Engineers. Then there are some regional communities. For example, there is European communities, and there are also communities in Asia, in the US, in Russia, in the former USSR things and stuff like this. But these communities, they mostly, in the most cases, they are just taking the standards, the world standard, and they adapt to the region. And these guys, for example, like DIN, German Institute of Standardization, or British Standard Institution, they are taking the international standards, translating them to, for example, to German language and adapting to the system. Like, okay, in the Great Britain, we are driving on the left side, and in Germany on the right side, right? So, and therefore, for example, this ISO 262 could be also adapted in Germany like DIN 26262, right? Okay, so, and these terms like reliability and safety, they are defined on these standards. As I already told, reliability is continuity of the correct service. Safety is absence of catastrophic consequences. So, but these are very simple terms, and of course in standards, everything is well defined. And for example, in the IEEE and IEC. Reliability, the ability of an item is a part of the system, to perform a required function, which is also a kind of the equivalent of the service, under stated conditions for stated period of time. This is important. Like reliability is the ability of something to perform its function under defined conditions, like for the car in the road or for the rover in the Mars. This is important. And under stated period of time, because every system fails and we define like, okay, my car will drive 6 or 7 years in the normal roads, and this means the reliability. So, and preliminary is the same in the other standards. For example, in the ISO, the ability of an item to perform required function under given environmental and operational conditions for a stated period of time. Or in military standard, it's used in the US, the duration or probability of fail-free performance. Fail-free performance is basically the same like the ability to deliver a function under stated conditions again. And same for safety. Absence of unreasonable risk due hazards caused by malfunctioning behavior of electrical and electronic systems, or functional safety is a part of the overall safety relating to equipment under control and equipment under control system, which depends on the correct functioning. So it's a little bit more complicated, of course, because this is, a part of the bigger standard. Okay, so, but we will talk mostly about this thing, and it's basically enough to understand this concept. Continuity of correct service, absence of catastrophic consequences. Okay, let's go next. Let's define what is system behavior, what is system state, because we need it for the further definition. So for instance, this is our system or even cyber physical system. And we see the system as a kind of a thing that provides service either to another system or to a user. For example, we have a speed sensor, and the speed sensor provides the readings of the speed to a driver. So, and it provides the service through the interfaces. And for example, here we have a service interface and we have the user interface. I mean, if we are here on this part, it means the interface of the service, and if we are on this part, it is the interface of the user. So, and delivered service, it's basically, do I have a, no. So we could define like the system behavior we can define as a sequence of states. Like we can describe the system using some variables. For example, if it is our speed, it is basically, okay, for example, inside the system we get some measurements that comes from the sensors on our wheels, for example, and these are the number of wheel rotation per second. Then we multiply it by the by the radius of the wheel and so on in order to get the speed. And this is a kind of the internal variables which are stored in our system. And the state of these internal variables is a current system state. And now we can see that some of these variables are internal, some of them external. I mean, to the user, we provide only the speed. So we are not providing, the number of rotation of the wheel during the second. And this number of the rotation of the wheel is basically internal variable, and the speed is external. So, and the system state is the set of this internal and external variable. But delivered service, it's only the sequence of external states. Okay, usually I'm using the whiteboard for that, but now it's a little bit complicated, but I hope you get it. Okay, system defined with variables, some of them stay inside, some of them goes outside. The state of these variables, the values at one time defines the state of the system. the sequence of the state defines the system behavior. The sequence of the state visible outside is basically the delivered service. Okay. Now we know that our system during the execution time provide service, and it should provide the correct service. Is delivered when the system service implements a system function. So it means that, for example, the system function is to provide the correct speed, and as long as the speed is correct, we are talking about the correct service. And at some point, the failure could happen because of something, because of some fault or some error. We could have a failure, and the failure is an event when the delivered service deviates from the correct service. And this is basically a point in time when the system stop provides the correct service. We call this point in time, we call it failure. So after that, after some time, the system can restore itself. For example, if the fault is not permanent, if the fault is transient, then it can just vanish or disappear by itself, or we can repair the system, and the correct service, we will have the correct service again. And here we are talking about the service outage is the time between the failure and restoration. And service restoration is basically the act when we restore the service of the system. Okay, correct service, failure, incorrect service. This is service outage, restoration, correct service again. Now, the thing is that when the system operates correctly, it operates correctly. When the system is failed, it can be failed on different ways. For example, it can, our speed sensor can produce, can give us no data at all. And this is one failure mode. It can give us noisy data when our, let's say, our speed will be oscillating by some around some value. This we call it noise. This is other kind of failure. Or, for example, it could be drifted, or like the error, mathematical error is reading is increasing by some reason. And these are several different failure modes. And this means that, okay, after the failure, we can jump from the correct service to the failure mode 1, then we can restore, and then because of the other failure, we can go to another failure mode. So now, the failures could have different consequences. For example, if the readings of the speed sensor is noisy, okay, it's bad, but it's not so bad. We can preliminarily know our speed. But if we have no speed on our display, this is more severe failure. And now we are talking about the severity. How bad are the consequences of the failure? And in different industries, there are defined in different industries in a different way defined the severity levels. For example, nuclear safety, they define the levels like from green to magenta, and like anomaly, incident, serious incident, and up to major incident. And they are well defined. For example, if we have a core meltdown of the nuclear power plant, it's definitely major incident, or maybe it is serious incident. But if, like in the Chernobyl, the nuclear and this radioactive waste goes outside, this might be defined as a major incident. And the same are defined, for example, in the ISO for the cars. And we can, let's say, each failure mode can be marked with this severity. And this is basically, some connection from reliability to safety. Basically, okay, the system is failed, and this is reliability characteristics, but depending on how it is failed, it becomes already safety characteristics. So yeah, like I wrote here, unreliability is the likelihood that from the correct service we jump to the failure. And if we multiply this probability of failure to the severity, that's how we can, estimate system safety. Okay. Now, dependability from error to failure. As I already told, we have three kinds of threats: failure, transition from correct to incorrect service, error, deviation from the correct internal state, and fault, cause of an error. So, as I told, for example, in the example of our speed sensor, the fault could be different. It could be, for example, the bug in our software that do the thing, or it could be the mechanical damage of some wheel sensors that provides us the original data. This is a fault. Then because of that, we are computing, for example, the number of rotation per second. And this is an error. This is something internal. As soon as we provide the wrong data, this becomes a failure. So, and that's how we are saying, okay, the system delivers us incorrect service. So, but between the fault and the failure, we could have some time. I mean, it could be that at some point in time, something bad has happened in the system, some fault appears or fault activated. And then the system is in erroneous state for some time. But as soon as we provide incorrect service, this is the point in time when the system failed. And this is the failure. So, and we always first have the fault activations, then we have an erroneous state of the system, and then we have failed state. So also, the system could be in so-called degraded mode. What does it mean? It could be that the system provides several services, like I think you can come up with many examples of that. For example, okay, even in our display in the car, we can see the speed, we can see the how many gasoline we are using per 100 kilometers, and we can see these rotations. So, and only if the system partially provide the incorrect service, we call that the system is on the degraded mode. Some of the services are provided, some of the services not. This is defined as a degraded mode. So, and now again about these faults, errors, and failures. And I want to explain these terms using this example. So, this is a mobile robot, and we are looking on it from above. And it has an ultrasonic sensor in front to detect obstacles and to perform some avoidance. It has the sensors in the left and right wheels to calculate the speed. And then we have a kind of a software system that reads readings of the front sensor, reads the speeds from the left and right wheel, and it provides two services. First, it computes the average speed of the robot, like a mean value between left sensor and right sensor. Then and basically this is the speed which will be provided. And it also takes the reading from the front sensor, which is the distance to the obstacle, and it computes time to collision. Time to collision is computed like front distance divided by speed. Yeah, logical. Now imagine that this is a software system, and by some stupid reason, instead of division, the developer put multiplication in the line of code that computes the speed. And this is a fault. It is a software bug, and it is a fault. This is original design, this is our fault implementation. When the system is dormant, when we are not using it, everything is fine. As soon as we start the system, it operates, it reads the front sensor, left sensor, right sensor, and for example, it is 10, 4, and 6, and everything fine is up to now. But as soon as we execute this part, we store the variable equal to 20 instead of variable s. The value of variable s is now 20 instead of 5 because of this fault. And this we called fault activation. The fault was activated. Because of the fault activated, we have the difference in the internal state of the system. Up to now, we have not provided this output. That's why it is internal state of the system. And this is the difference. And this difference we called an error. Because of this error, we have another error because the value of t now is also different. And this we called error propagation. Because of one error, we could have another error. And at the end, when the readings go outside of the system fails to provide correct service. And that's why we have two failed services. And the system is not even on the degraded state, but on the failed state. Okay. You might mention, or you might notice that the failure is really depends on the system boundary. Let's say when the difference is outside, it is an error. When it goes, when the inconsistency of the system state is inside the system, it is an error. When it goes outside and becomes visible, it is a failure. So the failure depends on the system boundaries. Okay. Good. And also, for example, on this design is also there is another so-called design fault. So this was a software bug, and it is one kind of fault, and another bug, it is so-called design fault. Because, for instance, if our left sensor will equal to 0 and right sensor will equal to 0, then we will compute S, it will be 0, and then here we will divide, we will have the division by 0. So the system is completely faulty from this point of view. Okay. Again, this is a picture from this paper of Avicenius, and it's basically the same what I have explained. For example, we have two components. So, okay, it's a little bit more. It also explains the error propagation between the components. We have a component A. Because of the dormant fault of this component, we could have an error. Or we could have an error because some data to the component A was already provided erroneously. So it could be internal fault or external fault. Because of that, we could have internal error. And as soon as this error goes outside, this is a service interface. Component A provides data to the component B. As soon as it provides wrong data to component B, this is a failure of component A. And on the same time, the failure of component A becomes an external fault to a component B that relies on the service of component A. And because of that, we still have the correct service of component B, but as soon as component B provides wrong data to some component C or system and blah, 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 this becomes a failure of component B. So that's why the fault activation results in an error. Error can propagate either to another error or to the failure. And the failure of one component can cause the fault of another one. So that's how these three basic terms of dependability are connected: fault, error, failure, chain. Okay. Again, here in our example, now imagine that we have an external fault. The front sensor reading is erroneous. As soon as we read it, it is a fault activation. Because of that, we have discrepancy in the internal system state. And then when it becomes visible outside, we have a failure. In this case, if only this part is erroneous, let's say this error does not propagate to the robot speed, but it propagates only to the time of collision, and the system now in the degraded state or in the partial failure of the system. Okay, now we will talk about faults and the classification of faults. Okay, just be ready now. It will be a little bit boring because I'll just go through the tables telling you that there are the faults like this, like that, like that. It's quite boring, but we'll give you some ideas about fault classification. I'm not sure that you will remember it, but at least you will know that there is Lepre and Avicenus, and they have the papers that provide such classification. Okay. They classify the fault according to the next categories: phase of creation, system boundaries, phenomenological cause, dimension, objective, intent, capability, persistence. And for example, according to the phase of creation, it's either development fault or operational fault, depending where it was introduced, either during the development, like a bug, or during the operation, like a broken wire, system boundaries, and so on and so forth. The thing is that, okay, there is 31 combination of the things. So, for example, operational, internal, human-made, software, non-malicious, non-deliverable, accidental, and permanent fault is a software bug. The software bug is operational because it was developed actually occurred during service delivery of the use phase. I'm not sure here. This might be an error in my slide. I would say that the bug is a development fault because it was introduced during the development. It is internal because it is inside of the system. It is a human-made. It's not because of the nature. It is a software. It's not hardware. It is non-malicious because the software bug, let's say, if it was intended, then it is already, some hackers attack, and this is malicious fault. But if it is a bug, it is non-intended, and that's why it's not malicious. So, or also non-deliberate, introduced without awareness, and so on. It is accidental and it's permanent. It's stayed on the system. So, also now it is another slide from this paper. We have, for example, according to the phase of the creation, there are development faults, physical interaction, and then, for example, some examples like physical interferences, they are located here. So you see there are lots of combinations. So, and depending on the combinations, we could, classify the faults. Yeah, development faults, physical faults, interaction faults. Let's go through these classifications again. Well, the first classification is phase of creation. According to the phase of creation, it's either development faults or operational faults, because first we develop the system and then we use the system. And everything that happens on the development phase, it is stated here. You remember this thing, or this sweeper. And everything that happens during the use phase, it happens here. So development faults occurs either during system development, or it also can occur during the maintenance of the system. When the system was updated or repaired, it's also, we could call them development faults. Generation of procedures to operate or to maintain the system. And operational faults occur during the service delivery of the use phase. So, and here we are also talking about the maintenance, which is also defined in this dependability. And the maintenance also could be different. It's either deals with repairs or modifications. If it deals with repairs, and in this case, the maintenance, either the corrective maintenance, when we remove the faults which are detected on the system, or it also could be preventive maintenance, when we discover and remove dormant faults. I mean, reported faults which are already detected and we remove them, or we find out that there are some faults which haven't been activated yet, and then we trying to avoid failures in the future, and this is preventive maintenance. And also maintenance could be for the modifications, and here also there are further classification: adaptive maintenance or augmented maintenance. So, and also quite tricky thing in the dependability theory that there is maintainability and there is fault tolerance. These things are similar, but the difference is that maintainability is the ability to modify and repair the system, and this usually involves a human. I mean, we have a fault in the system, we need to repair it with a human, and this is a kind of maintainability. But if the fault is inside and the system has some, some backup, some redundancy to avoid failure under the presence of this fault, this is a fault tolerance. Yeah, the difference is that in the maintainability, the humans are involved. Okay, system boundaries. The faults can be internal or external, as I explained on this figure. It could be internal faults or it could be external faults. Phenomenological cause. Natural faults are caused by natural phenomena without human participation. Human-made faults are a result of human action. Hardware and software, it depends where the fault is originated. For example, the broken wire is a hardware fault, and some bug in the code, it is a software fault. It's not about where the error appears. For example, we also could have a software error because of some hardware fault, but it's where it is originated. So the next group is also a little bit tricky, and there is another special table explaining this. The guys really try to classify everything which is possible to classify. So 3 categories: objective, intent, capability. According to the objective, it could be malicious faults and non-malicious. Malicious are introduced with the malicious objective. Let's say the goal of the introduction of this fault, let's say I'm introducing this fault to harm the system. Okay. The second is the intent, like was it the result of a harmful decision or introduced without awareness? For example, if I'm a bad engineer, I can introduce a fault without awareness. But if I'm a good engineer, I could also introduce the fault because by my bad reasons, I want to make this system fail at some reason. And this is the difference. So and basically preliminary is the same as defined here. Accidental faults are introduced inadvertently, and incompetence fault are the result from lack of professional competence. So this is more or less defined here. Let's say human-made faults can be malicious or non-malicious. If it is malicious, it is for sure deliberate fault. If it is non-malicious, it could be a non-deliberate or it could be deliberate. And in both cases, it could be either accidental because of an accident or because I just don't know something because of my incompetence. So, and this is also, we will talk a lot about that. The faults can be either permanent or transient. And this is quite important because permanent faults are continuous in time. For example, let's say if some wire in our system is broken, it stays broken. But for example, if you have a software bug, it can be, erroneous value some reason, but on the next time we make it correctly. So it could be a transient fault. And also, for example, there are so-called bit flips, when in the computer memory one bit is flipped accidentally from 0 to 1. I mean, not accidentally, there are causes like, for example, radiation or heat or lowering voltage. So, and these are usually transient faults. I mean, okay, we have a fault during some time and then it disappears. Let's say the transient faults, they are, most of the hardware faults are transient and most of the software faults are permanent. I mean, if you wrote some bug in the code, it is permanently there, or if you create some bad design of the system, it's permanently there. But for the hardware, you know, because of the environmental effects, the fault can appear and disappear. And also there is so-called intermittent fault that appears and disappears rapidly, whereas permanent faults remains within the system if no corrective action are performed. So intermediate fault is a transient fault that appears in the sequence. So just transient fault can appear and disappear and everything fine. But intermediate, it means that, okay, it appears, disappears, appears, disappears. Another classification, which is not here, but also mentioned in these papers, are random fault versus systematic fault. Random fault occur at a random time during operation, typically due to physical processes such as damage or fatigue. System fault is often a result of an error in the specifications that can only be eliminated by a modification of the design and manufacturing process. Let's say in the hardware, we could have random and systematic faults according to this standard and many other standards. And in the software, we usually have only systematic faults, since software bug can only be eliminated by the modification of the code. Software doesn't degrade over time, and its failures are only activated because of the particular input sequences. Therefore, software faults are usually input sequence dependent, and the hardware faults depends on the environment and other things. Okay, that was about the faults, and okay, we started at 10, almost an hour. Yeah, I just want to finish the entire lecture today. And the next chapter is the classification of failures and errors, but I believe you already tired, and I want to show you one more example of failure, and this is also from the space industry. It was the launch of the Ariane 5 rocket in French Guiana. It was quite a long time ago in 1996, but this is also one of the classical failure. The rocket was unmanned, but quite expensive. And let's wait, it should be some boom. Just wait for it. So, and you see that the rocket lifts, everything's fine, but at some point you see the trajectory goes really in a wrong way, and then it was this big explosion. Basically, in the majority of the rockets like that, they have a self-destruction system. So let's say if the rocket see that the trajectory is really bad, it self-destructs. According to the safety reasons, there will be less consequences when we blow the rocket in the air, then it will, you know, get down to the earth and will be explosion on the earth. I think in the previous lecture it also was pretty much the same. The rocket have been blown up in the air. So what's actually happened? You remember in the previous lecture I told that it was a human factor and hardware fault, and these IMU sensors were introduced incorrectly. Here it was a software fault. The thing was that Ariane 5 has a legacy code from Ariane 4, but Ariane 5 was bigger and faster, But in the code, the guys have been used short integer to store some value. I don't remember exactly, but I believe I have. Okay. So you could Google it here. So they store some value. I believe it was acceleration, and they store it in the short integer variable. And the short integer variable is a 16-bit variable that can store value from -32 to 32,000. So the problem that it was okay for the old version, but it was not okay for the new version of the rocket because it was faster, and it was basically an overflow. And after the conversion, the number stored in the variable become negative. So we could even take a look. I just get the code. The original code was in ADA, but I have the code in the compiler. So you could see that I'm taking the long integer and I put this number there, and then I convert it to the short integer. And when I am writing out this short integer, because of the buffer overflow, I have -32,536, and this is basically what has happened. So the rocket thought, okay, some readings becomes negative, and it started trying to correct it and then blow up. So example of a software fault that has killed this very expensive rocket. And this was like in 1996. You can imagine what can be done with a software system nowadays. I will show you some examples later. Okay. We got through the classification of faults. Now we will go through the classification of errors and failures. And we start with failures. And failures are also classified according to the development failures and service failures. So, and basically, is everything correct with my recording? Yeah, that's fine. So depending on the phase, so basically here the failures are mostly classified according to the faults. I mean, development failures could be the failure of the system during the development. I mean, for example, budget failure, the allocated funds are exhausted before the system passes acceptance tests. Let's say we decided to develop the system, but we thought that it will be cheaper, and basically we ate all the money and the system was not ready. This is a development failure. Okay, schedule failure. The projected delivery schedule slips to a point in the future where the system would be technologically obsolete or functionally inadequate for the user's needs. So let's say if we decided nowadays, to produce some old phone, it will be like schedule failure. No one will buy it. And about the service failures, they are also classified according to the domain, detectability, consistency, and consequences. So the consequences goes from minor to catastrophic. Okay, let's start with the domain. Domain is basically a content failure, timing failure, performance failure, halt failure, erratic failure. So here are the definitions. So content failure, the content of the information delivered at the service interface deviates from implementing the system function. We are delivering wrong readings with our speed sensor. It is a content failure. It could be also timing failure. When we deliver the information too late or sometimes too earlier is also not good. The time of arrival or the duration of the information delivered at the service interface deviates from the implementing of the system function. Let's say if we will deliver the speed of the system, but not the current speed, but the speed 5 minutes ago, it's also kind of a failure, right? And there are more specific things like halt failure or simply halt. When the service is halted, external state becomes constant. Let's say we deliver like nothing, or it's also sometimes it's called like stuck at fault or stuck at failure. So, and then erratic failure, otherwise when a service is delivered but is erratic, behaving in a way that it's not regular, certain, or expected. So like halt means we deliver no service, and erratic means we deliver incorrect service and it is differently incorrect over time. Okay. Then detectability, signal failure, unsignaled failure. It's basically the idea, can the failure be detected or not? Like the detectability viewpoint addresses the signaling of losses of functions to the user. Let's say, can user detect that it is a failure or not? For example, if we receive incorrect readings from the speed sensor, okay, probably we see, okay, we are driving, but there is nothing on our display. We can detect this failure. But it's also could be like unsignaled failure, like we receive some readings, but they are incorrect, but we cannot identify it. And the detecting mechanisms also have two failure modes: signaling a function loss when no failure has occurred, and this is like false alarm or false positives, and non-signaling a function loss when failure has occurred, and this is unsignaled failure or false negatives. So consistent failure, inconsistent failure. Consistent failures, the incorrect service is perceived identically by all system users. It means that if we deliver the speed to several users, if the failure is consistent, it means that all the users will receive erroneous but equally erroneous values. If it is inconsistent, it could be like by some reason we deliver correct information to one guys and incorrect to another guys. Okay. And this what I already has mentioned today, it's about the severity. It could be the minor failure, like nothing really bad has happened, and there is a catastrophic failure. It means, a lot of people have been killed, environment is damaged, and things like that. So now about errors. Again, error, system state deviation from expected state that can lead to another error failure. Errors are usually classified according to the failures that they can cause. So, and let's say usually the guys classify faults because it's important to classify the faults in order to understand, okay, what kind of faults we could have on the system. And we also usually classify failures because, okay, system has failed, we need to predict the reliability, the severity of the things. Errors is something inside, and it's not really important to classify them, but nevertheless, there are some classifications. But usually either according to the faults or according to the failures. It could be like detected error and latent error. It's like, it is a little bit similar to the like signaled failure and unsignaled failure, but for the error. Multiple related errors, it could be that several errors are caused by the same fault. In this case, these errors are multiply related. And there is signal error that affect one component only. Okay, so errors, detection, latent, detected, multiplicity, either single or multiple related. Whether or not an error will actually lead to a failure depends on two factors. The first factor is that the structure of the system. For example, basically this means redundancy. Are there any redundancy or not? For example, in the planes, all of the sensors are triplicated. And this is done by the reason, because if one sensor is down, the other two will provide correct values, and we can do the majority voting. Like if we have 3 sensors, one sensor is incorrect, we can compare the values of the other 2, and we see, okay, these 2 agree and this one disagree, and we can say, okay, we are not using the value of the erroneous sensor, we are using the value of the other 2. And this is called redundancy. So we add additional redundant sensors, or we can add in the same part, we can add redundant controller, redundant actuator, we could have even redundant motors in the planes, like for example, usually these, planes with the propellers, they still can fly with one propeller, and this is a redundancy. And this is how the airs are masked because of the redundant structures. Interestingly, it could be intentional redundancy, like putting 3 sensors, it's for sure we done it on purpose, and we will cover it on the next lectures. But sometimes it could be unintentional redundancy. Let's say by some reason it could be like 2 sensors do different things, but also their values are depend on each other, and we could see that, okay, if this sensor gives us this value and this one disagrees, that there is something wrong. And the sensors have been introduced not to detect the error, but they still can detect the error. Okay, and this is about the structure of the system. The second one is the behavior of the system. So the parts of the state that contains an error may never be needed for the service, or an error may be eliminated. It really could be like we do a lot of things inside the system, but we are not using this information, and this happens all over. So it could be that, okay, for example, we have a sensor that provides readings each millisecond, but the controller uses only the information that comes each 10 milliseconds because the controller is slower than the sensor. And if we provide some erroneous reading between these 10 milliseconds, it just will not be used. I mean, we have error in the system, it's inside, but it has not propagated to failure. And this is, we can call error masking. Like we are masking, like masking the error. Okay. Probably last part of the lecture. I mean, no, not last part, but almost the last one. Means, there are 4 means in the dependability theory: fault prevention, fault tolerance, fault removal, fault forecasting. The most important one is fault tolerance. Avoid failures. Okay, not the most important one, but let's say in most cases we are talking about the fault tolerance. And we will have a separate lecture about fault tolerance. The idea of the fault tolerance is to avoid failures in the presence of faults. And again, these 2 guys, they have defined good structure for the fault tolerance as well. And the fault tolerance, they defined as 2 parts: error detection and recovery. So first we need to detect error, and then we need to recover. So, and there are error detection mechanisms and error recovery mechanisms, but the fault tolerance we will discuss in details later. Now let's talk about the fault removal. Fault removal can be done either in the development phase, during the verification, diagnosis, correction, or non-regressive verification, or it can be done during the operational life because of the corrective or preventive maintenance. Verification, there are different kinds, different methods, or group of methods, how we can verify that our system is correct. And there are like static analysis, theorem proving, model checking, symbolic execution, and testing. Testing is used in most cases when the system is ready. Static analysis is also used a lot, but I will cover this also later. So fault forecasting, it means that we estimate the present number and the future incidents and the likely consequences of fault. So it's also classified into the original or qualitative evaluation, and also to the probabilistic or quantitative evaluation. Okay, and there are different kind of methods how we can do the fault forecasting, and some of them we will cover later, like failure mode and defect analysis of fault trees. We will cover them in other lectures. Now, let's talk about other 2 things that are connected to dependability but are not dependability. And I'm talking about security and resilience. These concepts are also well known and they are linked to the dependability. Actually, even Adesinis and Lepre, they try to define security according to dependability. And they define the security is basically the security is the concurrent existence of availability, confidentiality, and integrity, meaning that if the system is available, confident, and integrate, so I mean it's ready to service, there is absence of unauthorized disclosure and absence of improper modification of the system, then the system is secure. So, however, security domain evolves. The guys and the security, these are different. Okay, it's basically two different communities. A community who treats with reliability and safety, these are one kind of persons, and the guys who are treating with the security, they are different. And this community are quite separated. And what I'm showing now, it is the view to the security from the dependability guys. And this is not really well accepted by the security. In the security, they have their own definitions, and basically they are more, connected to the real life. And this security definition from the dependability point of view, it's a little bit artificial. So, and there were, okay, Lepre, he was a great guy. He proposed this theory of the dependability, but let's say from my point of view and also from point of view of some other guys, security should be treated separately. And there are lots of critics because Lepre, he also published a paper of definition and defining security in terms of the dependability, but it was really criticized. It's not really well accepted. So security is separate. Now another thing is resilience. And this is a kind of a buzzword nowadays because, I mean, it has something to do with fault tolerance. Let's say earlier I would call the system fault tolerant, but now we are calling it resilient. And this is also kind of, in the first lecture I talked about the complex mechatronic systems and cyber physical systems. And this is also something like this. I mean, resilience is a recent concept. It's not very well defined as a dependability. In different communities. There are different definitions of the resilience, and there are communities like IRIS and Resist. Also, resilience are used a lot by the network guys who are developing networks and all this, now softwareized networks, and they define resilience is an ability of a network to provide and maintain an acceptable level of service in the face of various faults and challenges to normal operation. Basically, this is fault tolerance from dependability point of view. Let's say another point of view in the community, like if we have really intelligent fault tolerance, then it is resilience. I mean, if we just reboot the system with fault tolerance, but if we used, some artificial intelligent methods for detection and reconfiguration, this is resilience, And there were also even, the way how to connect resilience with performance and with dependability. There are two papers about that. And these are defined like resilience is the persistence of dependability when facing changes. Like when we are changing the system stays dependable, and this is the resilience. You see, different communities, different definitions. So, and there is no well done theory like in the way for the dependability. As I told, a tendency has been to use it in each specific community to indicate a more flexible, more dynamic, less perspective approach to achieve dependability compared to the common practices in the community. And here through the next slides, I will give you, let's say, the point of view to the resilience, which are acceptable in several projects where I took part, and it was defined like that. Like, imagine we have some system that goes through the mission, and the system jumps from the system operation states from one state to another. And all these states are nominal, and we start the mission and we achieve the end of the mission, and if everything goes okay, we stay on this nominal area. But we could have the fault, and because of the fault we could have an error, and the system is still operationing, but we are in erroneous state or degraded state. Okay, it's not really degraded mode because we are still operating, but there is some errors inside, and we could have error, and because of the error propagation we stay on this gray area. Also, the failure could happen when we have an error. At some point the system can fail, so we cannot tolerate error. If the system is fault tolerant, we stay here, but if not, we jump to the failure state, and the system is failed, and we are on the failure state. So sometimes we should not even have, further lines here. Maybe the system is already dead on this point, right? So, and the fault tolerance is basically the ability of the system not to go from the erroneous state to the failure state. And this can be done with different fault tolerance technique like redundancy, voting, spare. We'll talk about it on the next lecture. So, but it's different redundancy techniques or reconfiguration techniques that we are not jumping to the failure state. We detect error, we recover, we stay on this erroneous state, or even maybe we recover to the nominal state. So, but sometimes we could say that we are in the failure state. The system cannot provide the service, but the system is smart enough to come back to the nominal state. And this also another definition of the resilience, which I really like. Like, for example, the fault tolerance is the ability to stay in the erroneous state and not going to failure, but resilience, the ability, to reconfigure from the failure state and come back to the nominal operation. Like the system provides no service at all, and then because of the automatic reconfiguration, we jump back to the operational state. Let's say fault tolerance means we are not in the failure state, we just block the possibility to go to the failure state. And resilience is just, okay, we are in the failure state, but we can jump back to operation. Okay. Well, that's all for today. I want to finish with some conclusion. We got through different terminology and different terms such as faults, errors, failures, availability, reliability, safety, and so on. We also talked about resilience, security, and basically the lesson learned is that all these terms are well defined by the dependability theory presented by Jean-Claude Lepre, and it is now adopted and well accepted by the industries. Some of the industries follow it exactly. Some, it could be differences from company to company, from community to community, but this is the basic, the skeleton of the theory. So industrial standards follow these dependability principles. And however, the Lepre's dependability was mostly oriented to the computing systems, but this is the most closed theory that can be used for the mechatronic and cyber-physical systems, and is used, this theory. So it is dependability theory is the most general theory around these topics that is available. So I believe it makes sense for you definitely to remember what is fault, error, and failure, and how from fault we could have error, and errors can propagate, and then we could have failures. I suggest also to remember what's reliability and safety, and what is a fault tolerance. And for the fault tolerance, we'll have the separate lecture. The other classifications, you just need to know that they exist. And now you know that they exist, and you know that if someone will ask you to classify the fault, you can go to these tables and classify it. Okay, thank you so much. I think I will stop recording now and I can answer some questions.